Alrighty, hello and welcome to Graphing Rational Functions. As a part of your homework, you would have done many of these things in isolation, and we're going to go ahead and put them together into 4 different examples of how we would graph rational functions. To start with, in our first example, let's begin with a single rational function. Let's try r of x is equal to a 2x squared plus 7x minus 15. And to make that a rational function, we need a denominator on it. Let's do x squared minus 2x minus 15. Now, when looking at rational functions, we will need both the polynomial form here, that's p of x over q of x, d of x? P of x over d of x. So we'll both want the fraction form, and we will want this same form factored as much as we can get it. So if you look at the denominator, hopefully you can see the factors here, the multiples of 15, the factors of 15. That will add to give you a negative 2. This would be an x minus 5 and an x plus 3. As negative 5 times positive 3 is a negative 15, and if I add a negative 5 and 3, I do get a negative 2. We will also need the factors of a 2x squared plus 7x minus 15. This has a leading coefficient. The factoring is a little bit more difficult. We'll take the first times the last to get a negative 30x squared. From there, we will look for the factors of a negative 30x squared that when added together will give us a plus 7. For the variable, that will be an x with an x. For the numbers, a positive 10 and a negative 3 will indeed add to a positive 7. This gives us the 2x squared plus 10x minus 3x minus 15. Factoring by grouping, I can pull a 2x out, leaving me x minus 5. And from the second pair of terms, I can pull out a negative 3, leaving me with an x plus, 5 on that as well. That x plus 5 is then pulled out to the front, leaving 2x minus 3 as my second binomial factor. So, placing that in my numerator, I have an x plus 5 and a 2x minus 3. This completes the first and most important step. We must have the factored form. Once you have the factored form, we can do a couple of things. I like to go ahead and find our x-intercepts. Our x-intercepts can be found by letting y equal 0. This means that our r of x would equal 0, which would be the 2x squared plus 7x minus 15. We would put that over x squared minus 2x minus 15. In order to clear the denominators, we would multiply both sides by that x squared minus 2x minus 15, leaving us with 0 is 2x squared plus 7x minus 15. We, of course, have the factors of this. It is 2x minus 3, x plus 5. And once we know that factored form, each one of those factors gets a shot at 0. 2x minus 3 is 0, or it is possible that x plus 5 is 0. Solving this little mini equation, we have 2x is a 3, and x is 3 halves. This gives us our first x-intercept at 3 halves, 0. That is going to be a solution to the equation and a point on our rational function. Our second one is x plus 5 is 0, meaning x would be a negative 5. So negative 5, 0 would be an x-intercept, and x equal negative 5 would be a solution to our rational function. We also need to find our y-intercepts. The y-intercept is found when you let x equal 0. In order to let x equal 0, I will again use my r of x. Instead, my x is 0. So when my r of x is equal to 0, I'm simply going to put 0 in for all of my x values. 2x squared becomes 0, 7x becomes 0, and I have a minus 15. In the denominator, x squared becomes 0, 2x becomes 0, and I again have a minus 15. This gives me a negative 15 over negative 15, which is 1. So I have a I have a y-intercept and a third point at 0, 1. All right, once we've got our intercepts, now we need to figure out where our asymptotes are. We figured out at least 3 points on the line in this case, but because we have a rational function, they will have asymptotes. So our asymptotes are the boundaries. We do have 3 different kinds of asymptotes that we look for. The first one is the vertical asymptotes. These are boundaries along the x-axis. They are vertical lines. We find them by going to the domain. The domain would be restricted based on the factors in the denominator, which means we're going to have an issue at x minus 5, because if x minus 5 is 0, we have a discontinuity in the domain. That discontinuity is going to be our asymptote. So at x minus 5 equals 0, we know x is equal to 5. That x equal 5 will be our first vertical asymptote. Our second vertical asymptote will be at our second discontinuity in the denominator. X plus 3 is 0 could cause a problem, or will cause a problem. In order to solve for that, that will be where x is equal to negative 3. That is a second vertical asymptote. I don't have any more factors in the denominator, so this is it. Those are my 2 vertical asymptotes. Our horizontal asymptotes. Horizontal asymptotes are found by isolating the first term of both your numerator and your denominator. So I'm going to go 2x squared here, and I'm going to compare that to my first term in the denominator, which is the x squared. There are 3 separate cases. They all have to do with the power, or the exponent, on each of those leading terms. Because those are equal, in this case, the x squareds will cancel. That is to say, as our x values get larger and larger, that plus or minus 15 is not going to matter there at the end. And the 7x and the 2x are essentially going to become the same thing, so they too will be eliminated. And we'll be left with 2x squared over x squared. Well, those x squared values are essentially going to be the same. Well, they are going to be the same. So I will just cancel that and get a 2. That means that my horizontal asymptote will be at the line y equal to 2. This is horizontal, and it will go that way. Well, it will go left and right, horizontally, of course. The third asymptote that we look for is our slant asymptote. Now, the slant asymptote only occurs when your numerator's exponent is much larger than your denominator's exponent. So if we have a horizontal asymptote, we're not going to have that case. So there is none on this particular rational expression, right? So we found our vertical asymptotes, we found our horizontal asymptotes, we found we do not have a slant asymptote. The last thing that we look for here is, are there any holes? Holes in your rational function occur when you have a common factor in both the numerator and the denominator. This is an x plus 5 and an x minus 5. They are not the same. And a 2x minus 3 and an x plus 3. They are not the same. There are no holes here. Because I do not have any common factors, I do not have any holes. Alrighty, so now I'm going to take all of this information and I'm going to put it together in a graph. So I'm going to zoom out a bit. Look at my lovely coffee cup. Alright. Dun, 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 dun. Here we go. I'm going to sketch an XY axis. I need to make sure I have enough room to include both of my asymptotes and any x and y intercepts that I might have. I think I'm okay if I go 1, 2, 3, 4. I think that should do it. I might have gone too big. If it is, I'll cut it up here. Yeah, I think I can go a little bit smaller. So we're just going to bring this up because I will need the space later. Okay. All right. So I've got my x-intercept at 3/2, 0. Got a second x-intercept at -5, 0. I've got a y-intercept at 0, 1. So I can go ahead and plot those 3 points. I've got an asymptote at x equals 5. I've got an x asymptote at x equals -3. And then I have a horizontal asymptote at y equals 2. Good enough. There we go. All right. Now, we need to look at how our function is going to behave as it approaches each one of these asymptotes. This is part 6 and the behaviors. All right. I feel like I spelled that weirdly, but that's, oops. Sorry. We're going to go this way. You can see my notes off there to the side so that I do this right. I don't make an error when I'm talking. We know I've done that in class before. All right, so we're going to start by listing the factored form of our r of x here. This is going to be an x plus 5 and a 2x minus 3 plus 3 minus 3 over our x minus 5 and our x plus 3. We want to know what's going to happen to x as it approaches various scenarios. The first thing is we want to know what happens as our x values get smaller and smaller. So as our x's head to -infinity. We will also need to check the behavior at each of the asymptotes. We had an x equals -3 and an x equals 5. On the -3, we want to test the left side. So this will be a -3 coming from the left. We also want to test the -3 coming from the right. We have to consider what happens as our x values approach this barrier from the right. We'll do the same for the +5. We want to approach that +5 from the left, and we want to approach that +5 from the right. So each side of that of the x equals 5 of that vertical asymptote. Then the only thing to check is what happens if our x gets really, really big as x goes out into infinity. So I'm going to leave a +infinity there. All right. Now, in some schools of thought, they will test a specific point. My preference is to just test the idea of a point. So I'm going to look at a very large, or very small, I guess I would say, negative number. We did -3,000 in one class, so let's do that. And what we're going to do is as we look at each factor, we're going to put in that -3,000. I don't care what the actual answer is. We just want to know, is the outcome going to be positive or negative? So if I put a -3,000 in for x and I add 5, that's going to give me a negative result. If I put a -3,000 in for this x and I double it, it's still negative. If I subtract 3, it's still negative. That's going to give me a positive numerator. In the denominator, a -3,000 minus 5 more is still negative. And if I have a -3,000 and I add 3, it's still negative. Sign-wise, I'll have a positive divided by a positive, which gives me a positive result. What that tells me is that as my x's get larger and larger and larger, as my x values get smaller and smaller and smaller and smaller, my y values are going to approach the horizontal asymptote from the positive side of it. So my y values will approach 2 from above. Okay, if this had been negative, I would have said they were going to approach 2 from below, but this is positive, meaning the resulting number will be higher than y equals 2. Okay, now my x values are going to come in, and I have to consider what happens on either side of a negative 3. So if I go on the little side of a negative 3 or to the left of a negative 3, that would be, for example, a negative 3.2, something just a tad bit smaller than negative 3. I'm going to put that in for the x in each of the factors and look at the sign. So if it's a negative 3.2 and I add 5, that's going to be a positive result. If it's a negative 3.2 and I double it and subtract 3, it's still going to be a negative result. Negative 3.2 minus 5 more, negative result. Negative 3.2 plus 3, negative result. So what I have here is a negative over a positive, which is a negative result. What this tells me then is as my x values approach that negative 3, they're either going to be forced positive or negative, and this tells me they're going to be forced negative. So my y will go to a negative infinity. Looking at just this part, this tells me as my x's are coming from a negative infinity, they are approaching that negative 2 from above. This is my little whoosh there. We're going to approach negative 2 from above. As my x values approach a negative 3 from the left, my y's are going to go down to negative infinity. This has to swoosh, or that part of the graph will decrease quickly. Now, I'll do the next two. If I'm looking at negative 3 coming from the right, I want something just a little bit larger than negative 3, maybe a negative 2.8. Maybe that's the number I put in my brain. So a negative 2.8 plus 5 is positive. A negative 2.8, if I double it, is still negative. If I subtract 3, it's still negative. In the denominator, if I have a negative 2.8 and I subtract 5, that's negative. If I have a negative 2.8 and I add 3, now it's going to be positive. Here I have a negative result divided by another negative result, which is a positive result. So as my x's approach negative 3 from the right, it's either going to be forced up or down, and in this case, because I got a positive result, we're going to be forced up to positive infinity. I'll notate that with a lovely little pink swoosh going up along that line. All right, taking a look at my other vertical asymptote, x equals 5. As x approaches 5 from the left, we want a number slightly smaller than 5, possibly a 4.8. I'm going to put 4.8 in for the x in every one of the factors. So 4.8 plus 5 is still positive. 4.8, if I double it, is positive, and if I subtract 3, it's still going to be positive. 4.8 minus 5 is going to be negative, and 4.8 plus 3 is still going to be positive. I have a positive divided by a negative. The overall result will be a negative value, meaning as my x approaches that 5, the y values are going to decrease or go negative. There we go. Indication for myself, it's going to go negative. Now I'm going to look at 5 coming from the right. I need to know what happens as my x approaches from the right. I'm going to choose a number slightly larger than a 5, maybe a 5.2. Now, if I add 5 to that, it's still positive. If I double 5.2 and subtract 3, it's still positive. If I have a 5.2 and I subtract 5, it's positive. If I have a 5.2 and I add 3, it's positive. So my numerator is positive, my denominator is positive, and when I divide them out, I get a positive result, meaning as my x's approach from the right, I either go up or down. The values of y will either go up or down. Because I got a positive, it's got to go to positive infinity, meaning it's going to go up. All right. Lastly, I got to check what happens at positive infinity. So as my x continues to get larger and larger, moving positive direction, it's going to settle around that the horizontal asymptote. It's going to settle around y equals 2. Will it settle above that line or below that line? If I get a positive result, it's above. If I get a negative result, it's below. So a really big positive number, maybe we use 3,000 since we use negative 3,000 on the other one. If I add 5 to a positive 3,000, it's still 3,000. If I it's still positive. If I double 3,000 and subtract 3, it's still positive. If I take 3,000 and subtract 5, the result is positive. If I take 3,000 and add 3, the result is positive. Again, I have positive over positive, which is a positive result, telling me that y is going to approach that 2 from above it. Right? So now, with all of these behaviors, what I can do is put them together. Do you see how this is going to approach from the positive side and here it's going to go up? This tells me roughly what this graph is going to do here. It's going to follow as a curve that corner. If we look at the middle section, you can see how it starts way down low, but it has to go through this point 3/2, and it has to go through that point 0.01, and from there it's going to go up. Something like that. It doesn't need to be perfect. It's not going to be a straight line. It is a curve, but it does need to do that. The confusing one is over here on this part, because even though we're coming down and it has to cross that x-axis, in order to be above, this has got to go up and over. It's got to go up and over that horizontal asymptote, and that's fine. It can do that. You can cross a horizontal asymptote. You cannot cross a vertical asymptote. So my graph is going to look something, don't know exactly what, something like this. If I would like to refine it, to refine this graph, you can plot x and y points. I prefer to use the factored form here, but if I would like to refine my graph and make it a little better, or if I would like to test a few points and make sure I'm in the right area. For example, right here, you see how that goes above, and I'm not real sure about it. If I'm not real sure about it, I can add a few test points onto here. This was a -5. Maybe I want to check a -7. Or maybe a -8. I'll do -7. Let's say we want to check a -7. I just want to make sure that -7 is still above that horizontal asymptote. So I'm going to use the factored form because I find that quickest. -7 plus 5 is a -2. Times 2 times a -7 is a -14. Minus 3 is a -17. I'm going to divide that by -7 minus 5. That's a -12. Times a -7 plus 3. That's a -4. So I'm going to get a 34 over 48. And at -7, I'm at 34 over 48, which is about 1/2. That, do I have the negatives, positives right? Let's check. That'd be negative, that'd be negative, that'd be negative, that'd be negative. Yep. So I've got a positive 34 over a 48. That's about what, like 3/4? So we're somewhere around there. We're less than 1. Okay, so that's got me a little worried. So maybe I'll try, should I try -8? Yeah, let's try -8 and see what happens. Remember, I'm trying to check and see where is it going to land above a 2, because I need it to go over that line, not just up to it. So if I do a -8, I'm hoping it increases. So -8 plus 5 is -3. -8 doubled is a -16, -19 over a -13 times a -5. So what's that? That's a negative. Oh, that's a positive. So that's 57 over 65. Yeah, it's still not 1 though. It seems to be going, it's up, but it's still not 1. Okay, let's see if we can't jump up a little higher here. I'm going to try a -10. All right, so if I try a -10, that's going to be a -5 times, that's going to be -20 minus 3 is a -23. And that's going to go over a -15 times a -7. All right, so that's going to be what 1? Okay, that's going to be 75 in the denominator. That's going to be 115. Okay, so I'm at least above a 1 now. So yeah, it's not going to be real quick, but it does look like it's heading towards that that horizontal asymptote, and we'll come up above it. So, yay! I can keep checking if I want. Maybe try a -20 or a -30 and see if we get any closer. But we do want to see it go above a 2 at some point. All right. If I want to, I can check. Maybe you want to check a 2 or a 3 just to make sure it's going down. You can check any number you want. I don't usually check a whole lot because this is what I'm looking for. But you can keep checking numbers if you are concerned. If I do a 3, 3 plus 5 is 8. 2 times 3 is 6 minus 3 is 3. 3 minus 5 is a -2. And 3 plus 3 is 6. So this is going to be 24 over a -12. So that's going to be a -2. So at 3, it should have been at a -2. All that would do is just make me adjust my graph slightly. But it does demonstrate that this area should be below the line. All right? Okay. All right, let's try a few more and see if we can get through them any faster than that one. Oops. Here we go. For our second example. We'll do an r of x is equal to a 3x minus 24 over x squared minus 5x plus 4. All right, first thing we want to do is factor. So I'm going to pull a 3 out, x minus 24. Oops. Can you tell it's getting late? No, probably not, because I did the same thing in class. It's going to be x minus 8. And then my denominator, I have an x minus 5x plus 4. I can factor this into an x minus 4, x minus 1. So I've got that sucker factored. We want to find our x-intercepts. X-intercepts will occur where y is equal to 0. So that means 0 has to equal the function 3x minus 24 over x squared minus 5x plus 4. Or 0 is just going to be 3x minus 24. Solving that for x, I'm going to add 24 to both sides and divide both sides by 3. This gives me the first point of an x-intercept where x is 8 and y is 0. Whole point of the x-intercept. Then we'll look for the y-intercept. The y-intercept occurs where x is equal to 0. So I'm going to take my r of x and instead I'm going to do r of 0, giving me 0 minus 24 over 0 minus 0 plus 4. This is just a negative 24 over 4, which is indeed a negative 6. This gives me a second point where my x is 0 and my y value is negative 6. Finding both the x and the y intercepts. Fourth thing is finding the asymptotes. The vertical asymptotes occur where you have incontinuities in the denominator. In this case, it is where x minus 4 would be 0 or x equals 4. My other possibility is if x minus 1 is equal to 0. Then my vertical asymptote would be at x equal 1. The horizontal asymptotes are found by looking at our leading terms of both the numerator and the denominator, 3x over x squared. In this case, the exponent on the numerator is a 1, and that is less than that of the denominator, which is a 2. This means that as our x values get incredibly large, excuse me, the value of our denominator will quickly overtake the value of the numerator and will go to 0. So our horizontal asymptote will be the axis where y is equal to 0. Our slant asymptote does not exist in this case. There is none. We don't have one because if you have a horizontal asymptote, you will not have a slant asymptote. The slant asymptote requires that your exponent in the numerator be more than the exponent in the denominator. Here we've already said it's less, so a slant asymptote cannot occur. We identify holes by looking at the factored form and identifying any common factors in both the numerator and the denominator. Since there is no factor in the numerator that is also in the denominator, we have no holes here. We know we don't have holes. All right, this is enough work to get us started. I need to be able to graph 8, 0, and 0, negative 6. So when I draw this, I'm going to make sure I can do 8, 0. And I need to make sure I can do 0, negative 6. I have 4 and 1, so that's good. Okay. 8, 0, 2, 4, 6, 8, 0. 0, negative 6, 2, 4, 6. I have vertical asymptotes at x equal 1. And at x equal 4. I have a horizontal asymptote at y equals 0. That is simply the axis that I'm going over right now. All right, with this done, all we need to do is look at behaviors to get the general H-A-V-I-O-U-R-S. Okay, so our behaviors will take the factors 3x minus 8. And I have an x minus 4, x minus 1, and I will look at them as x approaches a negative infinity. Then I need to do each of the asymptotes from either side. One from the left, one from the right, 4 from the left, 4 from the right, and then I need to do also a positive infinity. Oops, I'm going to probably smush over my own work here, but that's okay, we'll get it. All right. Now, again, for negative and positive infinity, we are looking at how it affects the horizontal asymptote. For the rest of these, it's how it affects the vertical asymptotes. So as we approach from the left and from the right. For a negative infinity, I'm going to use a big negative number or a low negative number like negative 3,000. And then I will simply look at the outcome of the signage. If I take a negative 3,000 and subtract 8 and multiply that by 3, I don't know what number it will be, but it will have to be negative. A negative 3,000 minus 4 is negative. A negative 3,000 minus 1 is still negative. I will have a negative divided by a positive, which is a negative result. This tells me that as x gets very, very large, the y value is going to approach the horizontal asymptote. So y is going to approach 0 because it's negative from below. So y is going to approach 0 from below. All right, let's do it for the vertical asymptote. Same idea. I need a number slightly left of a positive 1. Maybe a 0.8 will work. And again, I'm only paying attention to the sign. I don't need to know the actual number. If I have 0.8 and I subtract an 8 from it, that's negative. Multiplied by 3, it's still negative. If I have a 0.8 and I subtract 4, I will get a negative answer. If I have a 0.8 and subtract 1, I will have a negative answer. This tells me that as my x approaches a positive 1 from the left-hand side, it's either going to go positive or negative. In this case, I got a negative result. So my y will have to go down. Forced with the choice of going up or down, my y will go to negative infinity or down. If I look at 1, okay, so what do I got? This is negative from here. We're approaching 0 from below. Here we got to approach x equals 1, and it's going to go down as it gets closer and closer to that. All right. Let's look at this middle section. Let's approach 1 from the right-hand side. So I need a number slightly bigger than 1. Maybe a 1.2 will work. So if I have a 1.2 and I subtract 8, that's negative. Times 3, still negative. If I have a 1.2 and I subtract 4, that's negative. If I have a 1.2 and I subtract 1, that's more than 1, so this is going to be positive. I have a negative divided by negative. That is a positive result. So my y will go to a positive infinity. All right, so as my x approaches that x equal 1 from the positive side, it's going to go up to positive infinity. All right, let's look at the negative 4. I'm sorry, 4, but we're coming from the negative side. So instead of 4, I want something a little bit smaller, maybe a 3.8. So if I do a 3.8 and I subtract 8, that's negative. Multiply that by 3, it's still going to stay negative. 3.8 and I subtract 4, it's still negative. 3.8 and I subtract 1, that's positive. So now I have a negative divided by a negative and a positive result, meaning y is going to approach a positive infinity. So as my x values approach 4 from the right, it's going to go up again. So on both of those, it goes up. As we approach 4 from the right, I feel like I said right when I should have said left. As we approach 4 from the right, we'll need a number a little bit bigger than 4, like a 4.2. So 4.2 minus 8 is negative, times the 3 is still negative. Now I'm going to put the 4.2 into the denominator factors. 4.2 minus 4 is going to be positive. 4.2 minus 1 is positive. So I have a negative divided by a positive, which is a negative result. So my y values, as they approach 4 from the right, are going to go down towards negative infinity. This is going to go down. All right, then I need to do, I'm over my work. Then I need to do a positive infinity. Positive infinity here is going to hover around the horizontal asymptote. And I'm trying to determine if it'll go above that asymptote or below it. So a really big positive number might be 3,000. If I subtract 8, it's positive. If I multiply by 3, it's still positive. If I do 3,000 minus 4, it's positive. 3,000 minus, so this is going to be positive. This tells me that my y is going to approach that horizontal asymptote from above. Wait. Yeah, from above. So, like that. Okay. So now to fill this in. You will see here that it goes up in both directions. This indicates a parabola. That parabola is not going to cross the x-axis. How do I know that? If it had crossed the x-axis, I would have had an x-intercept. If it crosses that x-axis, I've got to have intercepts. I don't have intercepts, it's not going to cross the axis. Within this section, it's just going to be that parabola-looky thing. Okay? Over here on the left side, the graph is coming from down. It's decreasing and it's going to go up. And it has to cross at this intercept. That's the whole point of having that point there. I know it's got to cross there. Now when it does, at some point it's going to bounce. And it's going to approach that asymptote again. It's going to approach it from above, which is exactly what we got here. It has to approach from above. If I look at the section to the left of the vertical asymptote, you will see that coming from there, it goes down. I've got to cross through, we miss it because of my work. I've got to cross through that y-intercept, and it's going to keep going, and it's going to approach the horizontal asymptote from below. That's what I've got here. It's not going to cross that horizontal asymptote. It's going to stay below it as it goes into negative infinity. And this gives me a quick graph of the rational function 3x minus 24 over x squared minus 5x plus 4. If I want to refine this, I can test numbers in each section, x values in each section, to get a better idea. For example, does this come this close, or is all of this way up here between those asymptotes? I don't need you to do that for me. I just need this general directive as to what it will look like. Okay? All right. That one went much faster. Shall we try a third one? Okay, let's try a third R of x here. Here's our third one. We'll do example 3, and this guy says R of x is equal to x to the third minus 2x squared minus 3x all over x minus 3. Now, just like before, we want to factor first. Notice you can take an x out of all of those, leaving us with x squared minus 2x minus 3 over the x minus 3. Now, can you factor this more fully? Is there a pair of numbers that when multiplied will give you a minus 3, but when added will give you a negative 2? And indeed there are. This will be x times x minus 3 times x plus 1. This would go over the x minus 3. Some of you may notice that you have x minus 3 in both of those. That is true, you do, and that particular discontinuity tells us we have a hole. So let's do the others and come back to it. All right, so the second step we usually do is find our x-intercepts. To do that, we let y equal 0. You may have noticed that that just ends up being the numerator. So we're going to use the factored form of our numerator. So 0 could be x, or an x minus 3, or an x plus 1. I have not canceled out that x minus 3 because I need it for my, I need it in order to calculate my whole, where the whole is. So I'm going to keep it all together until the end. This means that our x could be 0, or it could be that x minus 3 is 0, and x is 3. Or x plus 1 is 0, and x is negative 1. This gives us a 0, 0 as an x-intercept. It gives us a 3, 0 as an x-intercept, and it gives us a negative 1, 0 as an x-intercept. Our y-intercepts occur where you let x equal 0. Oh, whoops. So instead of r of x, I'm going to do r of 0. This is going to give me a 0 minus a 0 minus a 0. Do you see the numerator is just going to be 0? I'll write it out. 0 minus 0 minus 0 all over a negative 3. That's just going to be 0. So I have a y-intercept at 0, 0. Okay, we want asymptotes. To find the asymptotes, the vertical asymptotes are where you have a discontinuity in your denominator, x minus 3 if that is 0. So our vertical asymptote would be at x equals 3. The horizontal asymptote. Horizontal asymptote, again, looks at just your leading coefficients, numerator and denominator. This would be x to the third over x. Technically x to the first. Do you see how that 3 is bigger than the 1? That indicates that there is no horizontal asymptote. So we will not have a horizontal asymptote. Okay. Will there be a slant asymptote? Well, if there's not a horizontal, then there's a good chance that there is a slant. But in order to have a slant asymptote, your n, or higher, your numerator's degree, needs to be 1 from your denominator's degree. So because 3 is 2 away, there's not a difference of 1 here, there is no slant asymptote as well. All right, we do need to check for holes. If you have not already noticed, there is a common factor, that x minus 3. So there is a hole at the common factor. So x minus 3 would be a hole. So x equals 3 is where the hole is. If x is equal to 3, then we'll find our y by putting 3 in for the remaining factors. So we'll use y is x, x plus 1. So that's going to be 3 times 4, which is 12. So there's going to be a hole at 3, 12. I shouldn't say the hole at the common factor, although hole sort of. The point of the hole is at the point 3, 12. Okay. Now, because there's a hole there, we do need to recognize that this is going to be a hole and it's not going to be a vertical asymptote. That doesn't always happen. Since our only vertical asymptote is also where our hole is, that negates that vertical asymptote. If there were other vertical asymptotes, we would need to include them, but we're not going to be using this vertical asymptote because it turns out it's actually a hole. It also means that over here, we're not going to be using this particular solution because it's a hole. So this x-intercept we won't be using. Because we don't have a vertical asymptote, and we don't have a horizontal asymptote, and we don't have a slant asymptote, I don't need any behaviors. Not in the same way. I suppose I should check my end behaviors, but that's way easier than doing all of the rest. All right, so let me draw my graph in here. I don't know if this is enough room, but we'll say it is. I've got a -1, 0, and a 0, 0 as the two intercepts that I need. I've got a hole at 3, 12. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a hole. I'll use an open circle to indicate that hole. And then I guess I will look at some end behaviors. But the behaviors that we are going to look at are just at the end. Because I don't have any asymptotes, I'll do x. Yeah, I can do x minus 3, x plus 2, the factored for x plus 1, sorry, over x minus 3. And then we'll take a look at what happens as it goes to a positive infinity and to a negative infinity. All right. So if we compare a negative infinity first, as x goes to negative infinity, that's going to be a negative times a negative times another negative divided by, okay, so I get a positive outcome. So my y will go to positive infinity. I don't have any asymptotes, so it can't hover around an asymptote. It's going to go up to positive infinity. For a positive infinity, very large numbers, that x is going to be positive. If I subtract 3, it's still going to be positive. If I add 1, it's still going to be positive. And if I subtract 3, it's going to, so I've got a positive over a positive, we got a positive. So y is going to go to positive infinity. If my y values have to go up and up, this indicates a parabola. So I'm going to make sure I use the hole that I had there. Right, there's the hole. It's going to come on down. At some point it's going to turn and go back up. And I essentially get, it's going through the 0, not through a hole. And I essentially get this graph with a hole at 3, 12. That's it. I've done the graph. It turned out to be a rational expression, but because it ended up being degree 2 in one of the factors, I didn't have any vertical asymptotes. So that worked out kind of slick. All right. And the quickest of all of them so far. Let's try this one, which I believe is a slant asymptote. So this is the fourth example. We're getting quicker as we keep going here. So I've got an r of x is x to the third plus x squared over x squared minus 16. I'm going to factor this out first. X squared times x plus 1 over an x minus 4, x plus 4. And that is first and foremost my factored form. Now I want to find my x-intercepts. Those occur where y equals 0. And if you had not noticed, it ends up being the numerator, x squared, x plus 1. So either x is equal to 0, or the second x is equal to 0, two of them because they're x squared, or it could be the x plus 1 is equal to 0, in which case x would be a -1. This gives us an x-intercept of 0, 0, or it could be 0, 0 again, or it could be negative 1, 0. I know some of you are saying, Amy, why did you do the 0, 0 twice? This indicates a multiplicity. We talked about multiplicities a little bit on Tuesday. This is a multiplicity of 2. And it tells me that at this point 0, 0, my graph will resemble a parabola. Near this x-intercept, my graph is going to either open down or it will open up. And that 0, 0 is going to be at the vertex of that little mini parabola. So because it has a multiplicity of 2, right around 0, 0, it's going to resemble a parabola either opening up or opening down. Negative 1, 0 only has a multiplicity of 1. It only occurs once. It is not going to have that same indicator. It's just going to go straight through it. Y-intercepts occur when x is equal to 0. So this will be at an r of 0. Well, I have 0 plus 0 over at negative 16. That's just 0. So my y-intercept is just going to be 0, 0. Some of you have already figured out that if your x-intercept is at 0, 0, you will have a y-intercept at 0, 0. Plain and simple. All right. Fourth thing I like to look at is for asymptotes. All right. 3 different kinds. I say all right a lot. Vertical asymptotes occur where you have a discontinuity in the domain. Those are identified in a rational expression by your denominators. So where is x minus 4 equal to 0? At x equal 4. That gives me my first vertical asymptote. I also have an x plus 4 equal to 0 in my denominator. If x plus 4 equals 0, or if x is equal to a negative 4, that also gives me a vertical asymptote. Horizontal asymptotes occur, well, they don't occur. Well, they do occur, but they're identified looking at the first term. So I'm going to look at x to the third over x squared. Notice that 3 is greater than 2. This means that there is no horizontal asymptote. However, there is a difference of 1. So there is a slant asymptote. Because there is a difference of 1, 3 is equal to 2 plus 1. This allows for a linear difference. How do we find it? Essentially, we got to use long division. So I'm going to actually divide out this x cubed plus x squared plus 0x's plus 0, and I'm going to divide it by x squared minus 16. I don't need to divide it out all the way. I just need to find the linear and any b value. So here's what we're going to do. X squared to x cubed means I need an x. Multiply back, and I've got an x cubed minus 16x. From there, I want to subtract. When I subtract it, I'll bring the x squared down, plus 16x now. Why plus, Amy? Because we minused. A minus gives you plus. So now I'm going to do an x squared into an x squared. That's a 1. 1 times x squared is x squared. 1 minus 16 is a minus 16. And now I'm going to subtract. So I'm going to get a 16x plus 16 minus a minus is a plus. This quotient is our slant asymptote. The line y equals x plus 1 will represent our slant asymptote. Okay. So, now we got a graph. I need to get to 0, 0, and 1, 0, so that's not too bad. And then I've got 4 and a negative 4. Okay. All right, points to plot, 0, 0, negative 1, 0. I don't have a y-intercept because that's at 0, 0. I've got asymptotes at x equal 4 and x equal negative 4. I'm going over my own work, but we get it. And I have a slant asymptote at y equals x plus 1. Using y equals mx plus b, that's a plus 1 where I go up 1 over 1 for my slope. So it's going to be, Sean, can I use this? Yeah, we can use this little thing. It's going to be here. So this is going to be my slant asymptote along this slanted line. I think I got a little bit off track there. Okay. There's my slant asymptote. All right. In order to know what goes where, we need behaviors. All right, so here are my behaviors. My factored form is x squared, x plus 1, x minus 4, x plus 4. We'll start with negative infinity. We'll then do a negative 4 from the left. We'll do a negative 4 from the right. We'll do a 4 from the left. We'll do a 4 from the right. And then we'll do a positive infinity. Okay. Really big negative number, like a negative 3,000. If I square it, it's positive, because anything squared is positive. And if I add 1, it's still negative. In the denominator, a big negative number minus 4 is still negative. A big negative number plus 4 is still going to be negative. This gives me a negative over a positive, which is a negative result. Remember, when you have either a horizontal or a slant asymptote, these last two are telling you how it's going to affect that asymptote. So this means that y is going to approach the x plus 1 asymptote from the negative side. This is a tiny little one. It's going to go right in here. Here's your, it's got to be below that. Here's your slant asymptote or oblique asymptote, and it's got to be below that. All right, let's try the negative 4. A number slightly smaller than a negative 4, such as a negative 4.2. If I square it, it's positive. If I add 1, it's going to be negative. If I take a negative 4.2 and I subtract 4, still negative. If I add 4, it's still negative. So I've got a negative number. When we're talking vertical asymptotes, we're either going to go up or down. So this y value is going to go to negative infinity and go down. That means all of the action is right here, and it's just going to follow the curve there. It's going to go from negative, and then it's going to turn and go negative again. All right? What if I come at negative 4 from the positive side? This would be like a negative 3.8, slightly bigger than that negative 4. If I square it, positive. If I add 1, still negative. In the denominator, if I subtract 4 from this negative 3.8, still negative. If I add 4, now she's positive. So I've got a negative over negative, which is positive. So my y values as they approach a negative 4 from the right will go towards a positive infinity, meaning they're going to go up as they approach that negative 4 from the right. What about as they approach the next barrier, which is x equals 4? I'm going to approach that from the left. So that's going to be like a 3.8, a little bit smaller than a 4. So if I square it, it's positive. If I add 1, still positive. If I subtract 4, she's negative. If I add 4, it's going to be a positive result. So I've got a positive over a negative, which is a negative. My y values are going to go towards a negative infinity as they approach the 4 from the left. There we go. That tells me that in this center section, I'm going to come from up above, and it's got to cross at that intercept. Right? That intercept only has a multiplicity of 1, so it's got to cross here. But then what's going to happen at the other intercept, because it has a multiplicity of 2, we can see it's either got to turn up or it's got to turn down. This one is going to have to turn down. That's what it means. It's going to need to look like this. There we go. Do you see how that looks like a parabola that's been turned down? That's what we're talking about when we say it opens down. It's got to open down into the rest there. There we go. Now I've got that middle section figured out. Now I just need to know what happens over here to the right of the 4. So a little bit bigger than 4 is a 4.2. If I square it, it's positive. If I add 1, it's still positive. If I take that 4.2 working in the denominator and I subtract 4, it's positive. If I add 4, it's positive. This will give me a positive result, meaning the y values will all be going towards the positive infinity as we approach from the right? Yeah. As we approach. So I got to find that asymptote, and I'm going to go up as I reach it. Okay, now, as we go towards infinity, so as we keep going, our behavior is going to be dictated by that slant asymptote because it's the only asymptote out here anymore. So, really big number, like the 3,000 that we've been working with. If I square it, it's plus, positive. If I add 1 to 3,000, it's still a positive number. If I take 4 away, it's still a positive number. If I add 4, it's still a positive number. This gives me a positive result. And as for the asymptote, this tells me that as y approaches this x plus 1 asymptote, it's going to be above that asymptote. So here's my asymptote, x plus 1. It's not going to be below, it's going to be above. So it's going to be like this. And this hugs that corner in the same manner that it did down here. And here we have the graph, or an estimation of the graph, for the rational function x cubed plus x squared over x squared minus 16. This is what she looks like. Right. 4 good examples. Please let me know if you have any questions.